Hello, everyone, and welcome to the Helio Speaker Series, the first one of 2025. I hope you all had a good year after hopefully a lovely holiday season. Um, I just give you a very brief overview about Helios. Probably by this point, you're all very familiar with Helios. So Helios is a 5-year project funded by the European Union with the aim to standardize the care for hemoglobinopathies by bringing together experts in the field and by providing training capacity and networking opportunities. And whilst the focus is really on Europe, we do have over 200 members from all over the world. If you do want to find more, I suggest you have a look at our website, which is heliosaction.eu. On our website, you can also get an overview about upcoming speakers of this Helios Speaker Series. The next one will be Dr. David Williams. He will talk about his gene work. If you are interested in joining this webinar, you have to register for each webinar individually. So if you're interested, please register for this webinar as well. You can also find the recordings of past speakers, with Kristen Howell being the last one who spoke about the challenges in the transition of patients from pediatric to adult care, and Dr. Sophie Landskrom, who shared her health economics work. And today, I'm very excited to welcome Anoeska. Anoeska is a PhD candidate at the imaging department of Radboud University Medical Center in the Netherlands, and her work integrates artificial intelligence with natural language processing to enhance diagnostic decision-making using routine test results. And in her first study, she developed a machine learning model that automatically detects a broad range of hemoglobinopathies using routine blood counts from 8 labs in the Netherlands and Spain. And this model is now implemented in the laboratory information system. Before doing her PhD, Anoeska spent about 7.5 years in IT forensics at Deloitte, developing AI-based tools for text classification and anomaly detection. And today I'm very excited to welcome Anoeska, who will talk about her recent work on using machine learning to predict hemoglobinopathies using complete blood count data. Anoeska, thank you so much for joining us today. We're very
Uh,
excited to learn more about your work and look forward to your presentation. Thank you.
well, thank you very much. And thank you very much all for being here and for attending my presentation. I will share it anytime soon. So can you all see my screen at the moment? Yeah, okay, check.
Perfect, wonderful, thank you.
Yes, all right. Takes a second, yes. All right. So yeah, thank you all. I'm Anoeska Schipper, and I wish you a warm welcome to my presentation on machine learning and hemoglobinopathy diagnostics. The reason why I'm here today is that we conducted a large-scale multi-center project that focused on developing a machine learning model to predict hemoglobinopathies using complete blood count data. And we did that in collaboration with a lot of laboratories, mostly situated in the Netherlands, but also one from Spain. And yeah, well, first I'm going to take you to our laboratory, which is situated in a multi-ethnic society. And basically we have two pathways to detect hemoglobinopathy. So first we have the basic diagnostics. These are the complete blood counts. And we do 300,000 of them each year. And what we see is that 0.5 to 2% of them have a hemoglobinopathy. So the prevalence is quite low. But we can already see from these blood counts if there is an indication for anemia or other blood disorders. And we use more complex diagnostics, which always happens on the indication of the clinician, to detect the hemoglobin variants, to quantify them, and to detect alpha and beta thalassemia. And then, of course, these can be the high-performance liquid chromatography or the capillary electrophoresis or the PCR. So this is what we also do in a regular mainstream laboratory in the Netherlands. And sometimes we do blood transfusions. Yeah, and then the question, why is indicating hemoglobinopathy diagnostics difficult? Well, for example, and this is a real case from our data, we have Alfonso, he's 36 years. And what we actually see when we do a blood test that measures his complete blood count, and we see that most of them are actually within reference range. And normally, yeah, I can imagine that you don't indicate follow-up diagnostics for these kind of patients. However, he actually had a hemoglobinopathy, and what we also see that the pathology can sometimes mimic an iron deficiency anemia. And therefore, many scoring systems are developed. And this is actually an overview from Urechaga, which is an author from a hospital in Spain that is also included in our study. And she has made a very nice overview of the many scoring systems that are there. And these scoring systems are used to indicate follow-up diagnostics. And I actually have a question for you. I don't know how that works exactly, but maybe some of you use these scoring systems, and I was wondering if you do, can you maybe tell how to use them? Oh, sorry, or is it possible?
Does anybody have any thoughts on this, or should we give you a bit more time to think about it and then we can
Yeah, maybe we can
leave it
also
until later?
yeah, we can also
Wonderful,
maybe
thank
do that. Yeah,
Thank you.
and yeah, okay. Yeah, well, it is actually most of these scoring systems are used to detect one type of hemoglobinopathy. And concurrently, we see that more machine learning models are developed. However, combined, mostly are developed in a single center context. They lack external validation, or they are focused on specific types, such as beta thalassemia or alpha, or a specific hemoglobin variant. They are developed on relatively small cohorts, and when they are tested externally, we see that the performance drops. So the goal of our study was to build a model that detects a wide range of hemoglobinopathies, developed in a multi-center context using a large cohort. And maybe one step back, what is AI exactly? So what is machine learning? Well, AI, artificial intelligence, is the ability of machines to perform tasks that typically require human intelligence. And yeah, AI is also a bit of an overarching term that encompasses a wide range of technologies and applications. And it ranges from simple automation to advanced self-learning systems. An example of an AI model, I think quite a famous one, is random forest. And this is an algorithm that makes decisions using decision trees. And it averages these decision trees to make a more robust and accurate prediction. So for example, in the picture here, you see a fruit basket. And when you take a fruit out of this basket, then it tries to predict which fruit it is based on different decision trees, and it applies majority voting to predict the final clause. And one of the most performance metrics that is used to evaluate these kind of models is the area under the receiver operating curve. And this metric basically indicates how well the model is able to distinguish the positive from the negative clause, so to say. And when your model is doing a really bad job, then your outlook, so to say, is around 0.5, and then it's just like flipping a coin. So it's a random classifier. If it's really good, then it almost hits the roof and your ROC is 1. I take a sip. Yeah, so right now I'm going to bring you to our project, and I will walk you through what we did and the problems we encountered during this project. So I hope you're all ready for takeoff. And the first question, of course, that we had to answer is how could AI help in the daily laboratory diagnostic workflow? So the current workflow looks a bit like this. So we have a request from the clinician that sends routine blood test requests to the laboratory. Then the blood is analyzed and a report with blood counts is generated. And based on this report, we decide to apply diagnostic follow-up. And the first thing that we apply in our laboratory is a very easy rule of thumb. Namely, if the mean corpuscular volume is lower than 80, then we send the patient or we consider follow-up diagnostics, or if there is a clinical indication to do so. For example, the clinician sends this patient for follow-up diagnostics. And then we do either an HPLC or capillary electrophoresis to differentiate hemoglobin variants. And if the suspicion persists, then we also apply DNA analysis for determining alpha thalassemia. So what is then new? What we want is we want to screen all incoming routine blood counts on hemoglobinopathies using AI. So we use as an input the hematology report, and then if the patient has a high predicted probability, then we send it for a diagnostic follow-up. With, of course, the aim to reduce the missed cases. So what did our AI project look like? Well, usually you have multiple steps in an AI project. So you have your data collection, your data processing. You have to select, of course, the features that you want to use as an input. And you need to build your model. And of course, you have to validate it. And this is not a linear process, but it goes back and forth all the time. And of course, your data collection, you have to answer questions like which population do you want to include, how much data, what is your ground truth. If you have to process your data, you have to clean it, you have to harmonize it. For example, we use data from different laboratories that uses different reference ranges and different analyzers. When selecting your features, this is always like a trade-off, because if you include more relevant features, then of course your model performance will increase. However, if you use many features, then it gets more difficult to implement. And for model building, you need to divide your total data set into a training and tuning and into an internal validation set. So for training and tuning, you learn the model basically, how to distinguish both the positive and the negative class. And we used a logistic regression, which is just an easy formula that is very easy to implement, and an AI model that requires a programming language for implementation, but usually has a slightly better performance. Of course, you want to validate your model because you want to know if your model works in different contexts. For example, is it able to distinct hemoglobinopathies from iron deficiency anemia? And does it work in different laboratories? Well, the hardest part of our AI project, and I think for many AI projects, is usually the scoping and is also maybe the ground truth that you have to define. And yeah, I also had this question for you, like which patients actually fall into the positive category and which patients fall into the negative category. I found this not such an easy question, but it does affect how to develop and how to use your AI model and the data you're going to collect. And to dive a bit deeper, so why is it not so easy? Well, each laboratory has its own diagnostic process for applying hemoglobinopathy diagnostics. For example, some employ different hematological parameters. Some always apply alpha thalassemia diagnostics, and others do this only on indication. Some always apply DNA sequencing or the sickle cell test, and others don't. And this, of course, creates a data-related issue. For example, in the hospital where I am working, the decision to test for alpha thalassemia is made by the analyst or the clinical chemist, or is based on indication and primarily the MCV that we just talked about. And to be more specific, here I have an overview, and this is from our data. So on the y-axis, you see the alpha thalassemia patients, and there on the x-axis, you see the mean corpuscular volume. And we set a threshold of 80 and below to apply follow-up diagnostics. And actually what you can see here is that we missed then 25%. So that is quite a lot. And of course, this affects which data you're going to use, and either if you're going to use this kind of data in your training set or in your validation set, for example, to test your model. Okay, so maybe we have to break down the question, right? Maybe we should first focus on the positive category. So which patient can I include into this category? Are we going to include polymorphisms such as alpha triplications? Or what do we do with the clinically, I would say less relevant mutations such as an alpha 3.7 heterozygote genotype? And I think the question behind this is, do you want to know this? Do you want to detect these kind of people? What are the consequences of that? And what makes it also hard is that different methods are used per laboratory, and it starts already with the CBC analysis, so the complete blood count analyzers. There are different workstations used for detecting beta thalassemia and hemoglobin variants. But I think the diagnostics or the diagnostic workstations that affected our choices the most was actually for alpha thalassemia, because what we see here is that some methods detect 80% of the deletions, some 90, and then MPLA 95%, and some laboratories send it to Leiden University Medical Center to apply DNA sequencing to detect more rare variants. So this all affects, of course, which laboratories, again, you're going to include in your training set and in your validation set. And what is a positive patient? And how we did it, I will answer that question later, but I just wanted to make you think. And then, of course, we have the next part of the question. So which patients can we include in our negative category? Are these the routine patients for whom we do like standard hematological parameters? Well, of course, these are extremely low suspected patients. Because these are the patients that are coming in on a daily basis. And I'm actually quite sure that if we do this, then our classifier will hit the roof, right? Because if you have like a super negative population and a positive population, then you will get a very high outlook. But what does that mean? Or are we going to include the negative HPLC or capillary electrophoresis complete blood counts? Well, these are still low suspected, but not as extremely low suspected as the others. And we do have at least a diagnostic test report for them. Or are we going to focus on the negative HPLC and capillary electrophoresis plus a negative alpha-tal diagnostic test result? Yeah, that is something we could also do, but then we only include the patients that are a priori super high suspected. So what did we do? Well, in the end, we decided to collect data only, but from all from all patients who underwent hemoglobinopathy diagnostics. And we did that retrospectively from 2011 to 2023. And after processing, we had a little bit more than 8,500 patients. We decided to include all laboratories that did not conduct a comprehensive diagnostic evaluation in our training and tuning set, and for our internal validation. And for our external validation, we used the laboratory with the largest data set and who did everything in terms of hemoglobinopathy diagnostics, including Sanger sequencing. So we were very sure that these patients who are positive are really positive, and the ones who were negative are really negative. And this was a little bit harder to determine for these laboratories. So when we were working on this, of course, we had to extract all the results from these test reports, and they can actually be quite complex. And you can actually see some snapshots here, but we had like many variants of hemoglobinopathies. So in total, 106. And we decided to not, make a class for each group, but instead we bucketized them in order to build a classifier and to assess the performance. So that's how we did it, and you can also see that later on in the results. So here we have an overview of the complete blood count parameters, and we decided to include the hemoglobin of each patient in our data set, the mean corpuscular hemoglobin, and so forth. And what you can already see is that the people who are negative have a higher mean corpuscular hemoglobin, a higher mean corpuscular volume. A lower red blood cell count and a lower red cell distribution width. And for mean corpuscular volume, we can see that the positive patients have a lower value in mean value. And this was also the case for all the different classes that we included in our data set, except for sickle cell anemia. So for these kind of patients, the MCV was actually quite high, and we had 120 of them in our data set. So then the performance of our machine learning model and logistic regression. So what we did here is we validated our model on an external laboratory. That was, of course, not part of our training set, and the AUROC was 0.88, as you can see in this plot. And here you also see the contributions of the individual blood counts to our model. And we also looked at what threshold you have to select of the model to achieve a specific specificity or sensitivity. The logistic regression had a slightly lower performance, but still really good, I think. And again, you can see here the parameter contributions of the logistic regression. And basically MCH and MCV, you can use them interchangeably, and you see that MCH is suppressed by the ML model, and here MCV is suppressed by the logistic regression model, which happens when you regularize your parameters. Of course, we were also interested in the performance of our model on the individual classes. So for alpha 0 heterozygotes, the performance was 0.98, which is super high. And for the homozygotes, 95. For the alpha plus heterozygotes, the performance was a bit lower, which is, I think, normal, because the blood counts do not deviate as much as we saw here. Compared to the others, they have a more normal blood count compared to the other two. And for beta thalassemia, the AUC was also really high, 0.97. When we look at the other groups, we combined HBC, D, and E, and we had to do that because we did not have too many, not too high count of these in our data set, so we combined them. And then we can see that the AUC is 0.94, and for sickle cell 91, which is really good. And for HBS, it's a lot lower. And I think this is for the same reason as for the alpha plus heterozygotes. We also had a bucket of combinations. Combinations are, for example, HBS heterozygotes combined with a alpha plus heterozygotes. We had that in our data set very often. So these are the combinations, and we did not include polymorphisms like alpha triplications if it was only like an alpha triplication, but we did include them in our as a positive patient when they had, for example, a combination with a beta thalassemia. So it needed to have some sort of a clinical relevance in the end. So we also validated our model on the data set of Urechagha. Urechagha works in a laboratory in Spain, and she did an analysis of all the scoring systems to analyze the performance of alpha thalassemia versus iron deficiency anemia. And what we can see here is that the scoring systems achieve a AUC of 0.7 maximum, but most lower on her data set. And she had more than 400 alpha thalassemia and 1259 IDAs. And she also did that for beta thal, and we see here that the AUCs are of course a lot higher. And then we use her data set as another validation data set, so to say. And we applied our model on this data set, and both our models achieved an AUC of 0.95. And then we also made the distinction between alpha and beta thalassemia. And we see here that both models achieve a beta thalassemia of 0.97, which is really high and which is better than all the scoring systems. And for alpha thalassemia, it's 0.90 and 0.89, which is a lot higher than the 0.72 that we saw earlier on her data set. So then we were very happy with our paper and we sent it to clinical chemistry. And then one of the reviewers said, yeah, okay, really nice, but how effective are the models for screening? So, so we extracted 1 month of all routine blood counts, and we identify all patients that are known to have hemoglobinopathy. We enriched the data set with hemoglobinopathy cases up to 1% prevalence. Because in our hospital it was 0.5. The downside of this approach is, of course, that there will be more false negatives in this data set than in ours that we used, because you have patients that have never been tested. So what were the results? Of course, the AUC is super higher because your patient population, the negatives in your patient population are super negative. So this was 0.97, and for the logistic regression, this was 0.98. So it actually had a better performance. And maybe, I don't know, how am I doing in my time? Oh, actually quite good. So the reason was that the machine learning model was actually doing really well in picking up all these sickle cell patients. But when tested in real life, we saw that the sickle cell patients had a blood count that was very similar to intensive care unit patients. So sometimes it misclassified them as having an hemoglobinopathy, and the logistic regression was doing less well on the sickle cell patients, but therefore had a better performance on this data set. And I think the reason for this is that the sickle cell patients had a very different complete blood count than the other hemoglobinopathies. So the conclusion from our study, well, for sure we have the largest data set of hemoglobinopathies in the world. It was really a lot of work, but I think we are quite proud of it. And the good thing is that both models, they allow to screen daily on all routine blood counts on suspected hemoglobinopathies. So this is basically a positive predictive value approach. And you can also use it for more cost-effective use of alpha thalassemia diagnostics. So, for example, if you conduct a HPLC or capillary electrophoresis, and your patient is negative based on these results, and if it has a high predictive value, you can still conduct alpha thalassemia, or you can, if it has a low predictive value, you can decide not to conduct alpha thalassemia diagnostics. If you would like more information, the full article or assistance with implementation, then you can email me or Steve Kurstjens. He was my supervisor on this project. So you can email one of us. And then I would also like to thank you very much for your attention. And of course, I could not do this project on my own. I have done this with my incredible team. So yeah. And if you have any questions, then I'm happy to answer them.
Thank you, Anoeska. That was absolutely fascinating, really incredible. I mean, also how you explained it so well. You know, obviously the whole concept around machine learning and AI is sometimes a bit confusing for technical people, but it's really incredible. So we open the floor to questions. If you either want to raise your hand or put your question in the chat. Maybe I can kick off with a question, and I'm quite curious because I'm wondering like how many patients are sent for follow-up diagnostics based on your AI model versus the routine practice? Because it looks like, I mean, particularly for alpha thalassemia, obviously there's a really big benefit in using your model. And obviously we all obviously experience different practices in different laboratories. So I'm kind of wondering, do you suspect a higher rate of follow-up diagnostics based on your model?
Yes, I do, but it also really depends on how you're going to use it, basically. So you can set a threshold that allows for a higher specificity, or you can focus on a higher sensitivity. So that means that you want to miss less patients. So it really depends on how you want to use it, basically, because you also don't want to overload your analyst with many negative patients.
Yeah.
Yeah.
And I'm really curious, like, because obviously each laboratory had a slightly different approach. So how did your model deal with different laboratories having a slightly different diagnostic approach when it came to the data collection? Was that a challenge, or
Yeah,
how did you go around?
that was
Yeah.
indeed really a challenge. So what we did is that so all laboratories who did not conduct like the full approach were all part of our training set. And the laboratory who did everything was in our validation set to make sure that the people who were really negative were, they are of course in that external validation set.
Yeah.
We also assessed the performance for the laboratories individually in the internal validation set to see how well they did, and if they were really, if there wasn't a performance that deviated a lot from the external validation set, because then, you may have a problem, but that was actually not the case. So what we saw is that the model could deal quite well with the different analyzers used, and also with the different reference ranges. So that was really nice to see. And I think that's also because we had a lot of data. So it really, it could deal with this problem.
That's fantastic. Yeah. Thank you. We also got another question from Cesare Medri. Cesare, if you want to ask your question now, I think you need to unmute yourself as well.
Okay, thank you. Can you hear me?
Yes, perfect.
Thank you very much for the presentation. It was amazing, let me say. And I had a question which diverges a bit from the hemoglobinopathy team, or mainly we know that hemoglobinopathies not rarely go together with membranopathies and enzymopathies, and these pathologies might mess up with your complete blood count indexes. Did you screen out or did you look for these problems in your study?
Yeah, so you have like hemoglobinopathies and something else, right? But I didn't understand it actually.
Enzymopathies like PKD or G6PD or membrane problematic like spherocytosis, erythrocytosis, all these are known to come together with the hemoglobinopathies, and they can really mess up your complete blood count, like having a bigger NCV or having a darker, higher NCH or NCHC. So this might be a confusing factor that has to be screened out. My question is if you consider this in your study.
Well, to be honest, we did not looked in this issue particularly, but yeah, the question is, of course, why you would want to know this, because is it then the case that that these the patients with hemoglobinopathies have a different complete blood count then yeah, for this type, if you know what I mean?
What I mean is, if you have a patient with heterozygous beta thalassemia and membranopathy, then the NCD is hopefully higher than expected, and then it is in the negative bin, whereas instead of the positive bin where you would expect him.
Yeah. Yeah, we frankly we did not look into this, but we only had like the diagnostic hemoglobinopathy test report with the outcome, and I think, of course, you have like a range in which a specific type falls into. But yeah, basically the performance of the model was still quite good for all these types. So frankly, I don't expect any issues there. But again, we did not look into this. Yeah.
I do want to mess with you. It was a very fantastic study. You had fantastic results. I just want to say, if you in the future you look into the confounding factor, maybe have a look at all of that also, because
Yeah.
you could.
Yeah. Well, thank you very much for your question. I forgot to say that, but thank you very much.
Thank you, really appreciate it. We also got a few more questions in the chat. One from Petros Venturas, who's saying, thank you for the great presentation. Each country region has a different spectrum of globin gene variants, e.g. different distribution of severe mild variants. Did you observe important differences between centers and countries?
Well, of course, we had most of our laboratories were from the Netherlands, and we had Spain. But actually, I didn't see. Yeah, you have of course a different distribution of people indeed, but the blood counts did not deviate in that sense. So the patients who had beta thalassemia in Spain were very similar to those in the Netherlands. The only thing that you have to take into account, of course, is sometimes different measurement units are used. Yeah, and different reference ranges may occur. But what we see also from the validation that we did in Spain is that even though our model was trained on Dutch data, we could still pick up the thalassemias. For hemoglobin variants, we did not study this in other countries.
Thank you again. We also got a few more questions from Kisum Nitsedi. I apologize for the pronunciation. I thought that's more or less okay. Thank you very much for the presentation. How did you handle the imbalance in your data set since only 2% had hemoglobinopathies?
Yeah, that's a really good question. So that's why the last reviewer asked, okay, really nice, all these that you focused on hemoglobinopathy test results. But how does it actually perform in real life? So that is why we did the screening in the last part of the study. But what you can actually do is you can set the threshold of this model, and you can, if you have like a very low prevalence, such as we have in the Netherlands, then you say, okay, I set the threshold very high, so only a few people get an alert. But if you have a higher prevalence, then you can set that threshold a little bit lower, and you can calculate the best balance for this. Yeah.
Perfect. And we got 3 more questions from Kisung. Which software did you use, R or Python?
Oh, Python. Yeah.
Perfect.
For
And then
AI, I would say it's maybe a bit better. You have more opportunities there.
Perfect. And then the third question from him, or apologize, I'm not familiar with the name. Besides the CBC used as features, did you use any other variables like age, gender, sick or state, etc.?
Oh, really good question. Yes, we did. But actually, it doesn't make a difference. So we decided to kick that out because also for sex, we thought maybe, for example, hemoglobin, the hemoglobin reference range is different for males and females. But it did not affect our model. So it did not contribute anything, in other words. So we decided to leave that out. Also for the ease of implementation that I discussed earlier, the less parameters or features that you have in the model, the easier it is to implement for people.
Perfect, thank you. And the last question from Kisum is, was principal component analysis employed for dimensionality reduction, please?
No, we didn't because we had already not too many parameters in our model, and usually this is a very nice method if you have many parameters and you want to reduce that amount of parameters. So no, we didn't do that, and we also had already like an intuition of what was important. And you can also see that, of course, in the feature contribution. So you can also decide at that point to exclude features that are not important. Yeah. But yeah, it is also a method for distinguishing different groups. So it's not like you could use it. That is also an answer.
I apologize, I cut out for a very brief moment. So Petrus and Contouras had another follow-up question. I'm not sure if you just answered that one.
Okay.
How is the model performing for borderline cases, e.g. with the MCV close to 80? Does the performance change for such cases?
Wait, I didn't understand the first part.
So the question is, how is the model performing for borderline cases? For example, MCV close to 80.
Good question. What you see, it is we did not look at like if it is below or above 80, but more we looked at the different classes, so to say, and what we do see, by the way, is that that is maybe interesting. I have to recall it, but for example, for alpha thalassemia, if it's above 80, then it detects the alpha thalassemia patients actually quite well. So it's not like this cutoff that we had in our hospital where you would miss all these patients. What you do see on the other end is that if patients have a more normal blood count, then it gets more difficult for this model to detect these variants. But usually they also have less clinically relevant deletions or mutations. For example, the model had a slightly lower performance on HBS heterozygotes and the alpha plus heterozygotes because they have a more normal or negative, so to say, complete blood count than the positives. But yet then the implications of missing these patients are of course also lower.
Thank you again. You also got another question from Theo Zacharis. I maybe missed something, but to categorize patients into positive and negative groups, how
Yes.
about how about based on a clinical trial approach guidelines by defining positive and negative groups as intervention and control arms respectively?
So
So he's asking if a clinical trial-based approach,
yes.
based on subcategorizing obviously into an intervention group and a control arm, would complement the model, would help validate the model.
Oh yeah, so for prospective validation, for example, I think, right?
Yes.
Yeah. Yeah, that would be interesting. Yeah, you can of course then see what yeah how yeah what the exact performance is when you conduct the complete diagnostic workflow. But maybe I don't answer this question correctly.
Yeah, if you maybe could possibly clarify, I hope we got that correct. In the meanwhile, maybe just another note from Kisum is that thank you very much for addressing my questions. And also from Petrus Contouris, who says, thanks again for the great talk.
Oh yeah.
And
Well,
maybe in the meanwhile, I can just throw in another question, because in case people are interested in adopting your model at their local laboratory, what would you suggest? Can they get in touch with you? Is this
yeah,
model
they can get in
transferable?
touch. Yes. So right now we are working on deploying this model in our own laboratory. Look, a Python model is a bit more difficult than logistic regression, because for logistic regression I can just make a macro Excel with the formula in it, and then you can just use that. So it's really easy. Or maybe you can just make a rule-based formula in your own laboratory information system that is based on the exact weights of this logistic regression. So that is super easy. The AI model, or the machine learning model, is a bit more difficult to implement, because you would need a Python extension in your laboratory information system, or some sort of middleware that
Okay,
allows this. Yeah,
fantastic.
but you can email
Okay.
us if you want.
That sounds fantastic. Yeah, well, I'm sure obviously people are obviously still thinking about obviously more about your presentation. So if you want to get in touch with you, you obviously put your contact details in the presentation. The recording of this presentation will be posted online shortly. But unless there are any more questions, Anoeska, thank you so much for the fantastic presentation. Really fascinating.
Thank you for having me.
And Theo just put another note to say, that's all right. I'm trying to figure out some alternative approaches, paradigms to resolve the question with kind of group is best for positive and negative groups. The basic idea is whether the steps we follow when designing a clinical trial can be applied here. I think you answered that question before in saying yes. Whether the clinical trial design can be applied to further validate your model.
Yeah, I think yeah, you should as a next step. Of course, we did quite an extensive validation, but prospective validation is like a next step, and that's actually more or less what we are gonna do now as well. Depending on how you're going to deploy it, I think the risks are quite low, because you always conduct hemoglobinopathy based on indication of the clinician, and you only recommend follow-up diagnostics. So based on this model or not. Yeah.
Okay.
So it's an extra catch.
All right. Well, thank you so much once more again. I'm conscious we only got 5 more minutes until the end of the webinar, but unless there are any more questions, thank you so much once again. Anoeska, it was really fascinating, and thank you so much for breaking down everything into easily digestible language.
Thank you.
It's really easy to understand, and I'm sure we all feel really inspired to keep on following your work. It's incredible. Thank you.
Thank you. Okay.
All right then, everyone. Wish you a good rest of the day or evening, wherever you're based. And oh, we actually got another question from
Okay.
Carsten later. Oh, he waved his hand when he put it back down. Let me see. Carsten, would you like to ask a question? Or you just wanted to give a kudos to Anoeska for the great presentation? Oh, he just said, oh, he just wanted to say thank you and goodbye. There you go.
Well,
Thank you,
thank you.
Anoeska. So lots of thank yous in the chat as well. Fantastic presentation, and
Well,
really
thank you.
appreciate us joining today. Thank you. Take care. Bye
Okay.
bye.
Bye bye. Thank you.